Morning, everybody. We're going to expound on the correlation material we were talking about last class with Pearson's and with the just the general shapes of graphs and the concept of association. And so we're going to look at how you can draw different lines of fit today. So the first thing that we're going to look at is section 5C. We are in the orange book here. We're going to be doing lines of best fit by eye. Now, and basically that's just using estimation. So if there's strong correlation between two variables such that the correlation, the R, Pearson's coefficient is greater than 0.85, so the absolute value of it, so it could be like negative 0.85 or less or greater than 0.85. What we can do is we can draw a line of best fit by eye to illustrate the relationship. Now, in order to do that, what that looks like, the first thing that we have to do is we have to calculate the mean of the x and the mean of the y. So x bar and y bar there. Because what we're going to do is that this is actually going to anchor this line of best fit that we're going to draw. And what we're going to do is we're going to plot that x bar and y bar, the average x, the average y value. And then from there, all that we're going to do is we're going to sketch a line so that about half of the data is going to be above our line and the other half is just going to be below our line. So what we're going to do is we're going to use this data that we used for last class's bell ringer. And so again, this is with the discus throws and the ages and the distances. And so what I've done is I've gone ahead and calculated the mean point. You don't have to sit here and average them all out. Mr. Price saved us some of the trouble here. But what we do need to look at is how many data points there are, because now when we make this line here, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 data points. So whenever I draw my line, I should have 6 points above it and I should have 6 points below it. So I'm looking at it and I'm like, all right, 1, 2, 3, 4, 5, 6. So those are the 6 lines that we're gonna, or the 6 points that we're gonna get below this thing. So let's see here. That looks about right, and you can tell that I'm using a official ruler here. So let's see. So give or take that line right there, we've got 6 points above it. We've got 6 points below it. That is our line of best fit here. That is our line of best fit. And when you're doing it by eye, everyone can get a different line of best fit. Like they may not always be the exact same one, and that's okay. So we're going to revisit this here in just a second. But we're going to talk a little bit about interpolation and extrapolation. So when we're talking about data points, when we're talking about a scatter plot, the highest and the lowest data points in a scatter plot, we refer to those as poles. So if we use our line that we create, the line of best fit, to predict in between poles, we call that interpolation. Between poles, so inside of the poles. If we use our line here to predict outside the poles, we call that extrapolation or extrapolation, depending on how you want to pronounce it. So the interpolation relies on the fit of the data, but extrapolation is a little bit more unreliable, because extrapolation relies on the fit of the data and it assumes that the linear trend continues. So if we were going to talk about that using this previous discus example that we've been using, so the poles occur right here. So if you were going to draw some imaginary lines here, anything inside of these poles right here would be considered interpolation. Now, anything on the outside would be considered extrapolation. And again, kind of just to bring up why it is unreliable, is because this is a line that is continuing to go straight up, straight right, straight up. And eventually you're going to get to the point where you hit like you're 50 years old and your discus throw is still increasing. You're 60 years old and your discus throw is still increasing. Or 90 years old and it's still going up. And at some point, it stops being linear because you start getting older, you start getting a little bit weaker. And I mean, that's just the way that life works. And so whenever you're going to, if you're ever doing extrapolation, you need to ask yourself, does it make sense? Can I safely extrapolate in this circumstance? So going back to the other page. So we're going to look at an example here. So this is example 3 on page 114 in that orange book. And so basically what we've got here, we've got a table representing the amount of time that cars were left in the sun and the temperatures that were recorded inside of the car. And so what we want to do is we want to figure out the line of best fit. So the first thing that we're going to have to do is we're going to have to figure out what X bar and Y bar is. So we're going to add up all of these temperatures and then divide it by 6. So let's see, if we add all of these X's up, we're going to get 180 divided by 6. So that's going to be 30. So we got X bar is 30. And then Y bar, if we add up all of these temperatures right there, let's see, and then divide them, that is going to give us 38. So now, when we go to plot this point right here, X bar, Y bar, this is what's going to anchor our line of best fit. So let's see here. We're going to go 30 and then up to 38. So let's see, that's 36. I need to go a little bit above that. And that is our line right there. That is our line right there. And so what we need to do to draw this line of best fit now is we've got to draw a line such that we're going to have the same amount of points under it as we are over it. So let's see, is there a way? This would really be a good time to have a ruler rather than a sticky note. I'm just going to eyeball this. It is a line of best fit by eye anyways. So let's see here. We go roughly that way. This is a perfectly straight line, you can tell. And roughly that way. So when you're drawing these, do better than what Mr. Price just did. That was a terrible line. And so we've got a line going out that way. So this is our line of best fit. And so what we want to try to do is predict, we're going to use this to predict the temperature at 35 minutes. So we go over to like 35 here, and we go up, and then we're going to go over here. So give or take at 35 minutes, according to my line of best fit, that is going to be, we can call it like 44 degrees. And the thing is, depending on how you decide to draw your line, it may or may not be as accurate. It may or may not be as good because, again, we're graphing these. We can't expect them to be absolutely perfect, and that's okay. So then if we go over to 75 here, so we want to know, or excuse me, sorry. We want to know how long it's going to be for 55 degrees. So if we go to 55 degrees here, and we hit right here on this graph, and we go down. So according to the graph that Mr. Price has made, that's going to be 60, we'll call that, it's a little less than half, 64 minutes. And again, your graph may be a little bit different than mine because my scaling obviously isn't perfect. because I'm not doing this on graph paper or anything of that sort. So you just need to give it your best shot for these, because we won't be doing a ton of line of best fit by hands in this class. So then the last thing that we want to talk about is, are these predictions we made on C and D, are they reasonable? So think to yourself for a second, which one of those is more than likely to be reasonable? And so the one that's more likely to be reasonable is C, because it's interpolation. We went between those two poles, the lower ones. 35 minutes was in between this time span right here. So C is reasonable here. D isn't, because we did extrapolation. And as a general rule of thumb, we don't know for sure that trend is going to continue past the 50-minute mark. As a general rule of thumb, extrapolation is harder to do than interpolation. So that is how you draw a line of best fit by hand. That is how you approximate it, and that's how you go about doing that. So then the next thing that we're going to look at is we're going to look at how you use technology to do that. So to do that, what we do is we use something called a least squares regression line. And the issue with line of best fit by hands is what you all just saw. If you look in the book at the example, they have a little bit of different answers than I had, because they used probably some sort of computer software to graph it, whereas I was just truly going at it by hand, and it's going to vary from person to person. So to find the least squares regression line, which is the mathematical way of doing the line of best fit, you need to minimize the distance between the data points and the regression line, and we're going to take that distance and we're going to square it. However, in this course for IB, for applications and interpretations, they do not ask you to calculate it by hand. We're going to just use technology to do so. So you just need to know how to use technology to get this equation. So with that, though, what we need to understand is, so if you all have a question on the calculator stuff, please shoot me an email. I'm going to try to post a tutorial on how to do some of this stuff, in case you all, my understanding is some of you all have TI-84s physically, and it's a little bit different than the app that I've been using, and that's okay. We will work that out. So for the example for looking at how to do this by hand, we're going to look at, this is example 4 on page 116. Number 4, page 116. And so basically what we have here is we have a table representing the annual income and the average weekly grocery bill for a selection of families right here. And so the first thing that we want to do is we want to make a scatter plot for this. So as a reminder to you all, to make a scatter plot using your calculator here, you're going to go to Stat and you're going to go into Edit, and we're going to punch in our X values here, and then we're going to punch in the Y values. So I'm punching in my X values. There's a little bit of a longer list. 60, and then 64, and then 42, and then 50. So then we're going to punch in our Y values. 90, 60, 160, 190, 250, 110, and 150. So again, when we create a scatter plot on a calculator, we want to go over to second and we want to hit stat plot right there. And we want to make sure that we have turned that on. Make sure that your X list is L1, your Y list is L2. And so that should be good to go. But then the other thing that we need to take care of is the window. So if I hit second and window there, what I need to make sure of is that when we go to view this, that it's not an unreasonable window. So we got the X minimum here. So I'm looking here. So if it's income, let's see, it stops at 25. I always like to just start at 0. And then we'll go to, let's see, the highest is 64. Let's go to like 75. And we can go by 5s there. So then for the Y minimum, here we can go by like, let's see, we'll start at 0 again. And we can go up to a maximum, let's say 300, and we can go by 30s. So when we graph that, and let me get rid of that equation that we've got there. That's from my statistics class. That is our scatter plot there. And what we're trying to see is there a strong linear relationship between the income that somebody makes and their grocery bill? So we can see that there appears to be a positive correlation. Data is heading this way. So now to actually use the technology to find the regression, what we're going to do is we're going to go into something called a linear regression. So if you go to stat and you go over to calc here, you'll see linear regression right there, as well as a bunch of other regressions that you can do. So we're going to go to linear regression, and we're going to get that equation there. So linear regression, and this is of the form AX plus B. So we've got Y equals 4.178 minus, can't forget that X, excuse me, minus 56.695. That is our equation right there. And what we want to do is we want to figure out, okay, what does the slope mean here? And so as a reminder, so it's mx plus b. This a right here represents the slope. And if you want to think about this as rise over run, where the denominator is 1, so the rise would be the y coordinate. The run would be the x coordinate. So what this means, for every 1,000 pounds, so for 1,000 pound of income, we can expect a rise in a grocery bill of $4 or 4 pounds. I don't know what is cents for in London? Is it like pence? I don't know. Maybe I'm just trying to combine pounds and cents. So the way that we interpret this slope, the grocery bill is going to rise $4.17. I don't know what the unit is there. I'll have to look that up after this. For every $1,000 that it increases. And the whole thing that we can do with this model, once we've created this right here, is we can use it to try to make predictions based off of the data that we have. So like, for example here, we could say, all right, we're going to estimate the grocery bill with an income of 95,000 pounds. So with that, what we would do is say, okay, 95,000 pounds here. So we need to remember that our data was in thousands of pounds. So what that means that X is going to equal 95. So all we're going to do is we're going to substitute that into there. We're going to say Y equals 4.178 times 95 minus 56.695, and I'm just going to calculate that real quick, times 95 minus 56.695. So that is 340.215. And since that is Y, that's going to be pounds. That's a lovely L I've got there. And so then we can also substitute in Y values and work backwards. So if we wanted to say, okay, estimate the annual income with a grocery bill of 100 pounds here. So again, pound. So the grocery bill is Y. So we're going to say Y equals 100 here. And we want to figure out what that is. So we're going to say 100 equals 4.178x minus 56.695. And we've got to solve this equation here. So just a little two-step equation. I know it's been a little bit since we've done some algebra. So we're going to add 56.695 to both sides. We're going to get 156.695 equals 4.178. I'm going to divide those real quick. I am really low on room here, so I'm not going to write the division. 4.178. I'm not going to forget the X, though. So if you have a grocery bill of $100 here, your income is estimated to be 37.504 thousand pounds, or 37,504 pounds. So again, when we're doing these things, we need to think about, okay, which one of these was interpolation, which one of these was extrapolation. And as a rule of thumb, interpolation is usually pretty safe. Extrapolation relies on a lot more assumptions. So for D here, D was extrapolation because we went outside of the data set here. We had X was 95, and the furthest that X went up to was 60. And if you think about it, like there's going to be a limit to how much food that somebody buys. Even though the income will go up, you can always buy a nicer quality of food, but there's got to be a level out point somewhere. I don't know where that is. I mean, you can't have caviar for breakfast, lunch, and dinner. So D is extrapolation. So we're going to say that that is generally unreliable. And then E here is interpolation. And since R was pretty strong here, we are good to go. It's a pretty strong linear relationship. And one thing that I didn't bring up that I could have, so whenever you calculate that regression line there, R, that correlation coefficient that we talked about, is going to pop up. And that'll pop up if you have your diagnostics turned on. So if you go to mode and it's statistics diagnostics, make sure you have those on. And it will tell you what the R is to tell you if it's a good, strong linear fit or not. And so we're going to call it a day there today. And we will pick up on where we left off next week. But you all have a good weekend if I do not hear from you. And if you all need anything, please let me know. See ya.